So let's start today's lecture. Okay, so I see nobody volunteer for these problems. That's okay. We'll leave it open for some time. If there is no solution, then we'll move on to the other problems. Okay. So we talk about derived rules in natural deduction. And so I just introduced what are the derived rules. One was this modulus tollens. And basically, this is not the primitive rule. So even if you don't know this modulus tollens rule, you can still find the natural deduction proof without using this modulus tollens. But what it helps is some proof can be very short. So suppose you know this, and you want to use this fact. So actually, suppose you know this 1 and 2, and you want to use, you want to derive not phi. You can fill the gap, but we can actually make it as a macro. So once you know the first two, let's pretend that this is like a rule. You can actually derive this not phi directly. That's what modulus tollens is saying. Okay. The other rules were double negation. One of the other was double negation. So this was actually introduction. So suppose this rule were not given to you before. So suppose you know what is phi is true, and you have to derive not phi. But suppose you don't have this double negation introduction rule. How can you derive not phi using the rules that you already know, the other rules that you know? Again, you have to go back to the strategy. So what is the goal to prove? The goal has negation in front, right? What's the proof strategy for proving the negated goals? I wonder what will happen next week when you do the quiz. Okay? So this was covered last class. If your goal is to prove a negated formula, what is your strategy? Try to assume not phi. And if you can prove bottom, right? So forget about the other thing. So if you have negation of something, right? So to prove this, you can have negation of phi, and if you can derive contradiction, then you can derive not phi. Okay, so there's a table that I drew last time. You can go back and check this. Okay, so using the negation introduction rule for this box. Okay, so let's say 2 to maybe n minus 1. So this is 1, 2, n minus 1, n. Okay? So if you can prove the box, negation of phi was assumed, and somehow you derive contradiction, that means negation of phi is false, meaning that negation of phi is true. That's what this negation introduction rules say. The question is then, how can we go from 1 and 2 to n minus 1? How can you derive contradiction? What can you do? If you know phi is true, and you also know not phi is true, what can you derive? There's a bottom, right? This was called negation elimination rule. And in fact, this is all you need. So this was premises, and this is assumption. And there's actually nothing in between. Okay? So the proof is saying that given phi, let's temporarily assume not phi is true. Then you immediately get the contradiction. So not phi is actually false. Okay, so you get not phi. So this is actually fill the gap. But even if you don't know this, if you introduce this as a macro, this rule is saying that given phi, you can go directly to not phi, because every time to fill the gap, you can use this box to fill the gap. Yes.
So if you're deriving subformulas, say you have a not phi, would phi and not phi, are those equivalent, or are those two separate subformulas?
If you derive phi and you derive not phi, they are two different formulas.
Okay.
Right? Okay. There are two different formulas, but not necessarily very much different. So we'll get to that position soon. Okay. All right. So the other rule is proof by contradiction rule. And we saw a rule like similar to this rule before. And that was when you assume phi, okay, and derive bottom, okay, what can you derive? Negation of phi. So this is a negation introduction rule that we just used in the previous slide. The PBC rule, proof by contradiction rule, is very similar, but it starts with the negated formula. So given the negation, and you somehow prove a contradiction called bottom, then you can derive phi is true. Okay? So suppose you're given this thing. We want to prove phi. Okay? Now, from this box to go directly to this phi, this is what the PBC rule is saying. But suppose PBC rule is not there. Still, we can prove it using the other primitive rules. So let's see how we can do, how we can fill this gap. Okay? So using this negation introduction rule, what can we derive immediately from this? Not phi, from proving not phi, and we derive bottom, what can we derive right after this? No? Look at the pattern. If you start with phi and derive bottom, you get not phi. Now, substitute not phi for phi. Then what should you derive here? Not phi, okay? So you get that not phi. If you start with not phi, then you should add negation. That's what negation introduction rule is saying. But we want to go from not phi to phi. What can you do? So from here to here is negation introduction for line 1 to n. Okay? And from here to here, so this is n plus 1. How do we go from n plus 1 to n plus 2? And this is just double negation elimination. Okay? So that's to line n plus 1. So the only step that is missing is this. Okay? But if you want to go from here to here, you can always insert these primitive rules. Okay? So let's just make it as a macro. This one pretending that this is already skipped. So we can go from line 1 to n to directly to n plus 2. That's what PBC rule is allowing us to do. And this is called proof by contradiction. So if we want to prove some claim phi, one of the technique here is proof by contradiction, meaning that let's try to assume for the sake of contradiction, phi is false. Okay, you have to prove phi is true, but assume temporarily that phi is false. That's what line 1 is saying inside the box. Okay? And with that assumption, you derive bottom. Okay? That means your assumption is actually wrong. Not phi is true is actually wrong. That means phi should be true. Okay? So that's the proof technique. And we will actually use this technique quite often. Okay? So to prove phi is true, what you can do is let's assume temporarily phi is false, okay, and derive contradiction. Now, note here that we are using the box, meaning that not phi is not established as true. We are just assume temporarily that this is true. So having the not phi inside the box and outside has totally different meaning. Okay? All right. The next one is law of excluded middle, and I gave you a hint in the Piazza. One of the question problem, you have to use this law of excluded middle. Okay? Now, what this rule is saying is you do not need any premises. Okay? You can just use this formula at any moment in your proof, phi or not phi. Okay? Anywhere in the proof, you can write phi or not phi. Okay? So, for instance, you're writing some proof, and you think that you need something like this one, you're allowed to do. Okay? Because it doesn't require any other formulas to be established. Okay? Typically, this rule is useful when you have to use OR elimination. Okay? So when you have to introduce two cases, for instance, case 1, P is true. Case 2, not P is true. Okay? And regardless of this case split, if you can derive the same conclusion, then that conclusion can be true. Okay? So this is the derived rules, but I'm not going to show you how this was derived from the primitive rules. The proof is not too long, but I guess it might be better for you to go over the textbook to read this proof. So I'm not going to bore you with this part today. Okay, but instead, I'm going to use this rule to prove this fact. So P implies Q can derive not P or Q. In fact, they're actually equivalent. You can also go assume not P or Q, then derive P implies Q. However, let's just look at only one directional proof. So what is the first line that we have to write? P implies Q. What is the last line that we have to draw? Write? Not P or Q. Okay, so we are done. Then the question now is, how do you go from 1 to n? And this is actually not simple. Okay? How do you prove the disjunction, not P or Q? So let's, before actually we try to prove this natural deduction, try to reason informally. Okay? Because that will actually help you to write down the complete proof. In fact, that applies to your homework too. If you try to blindly prove the natural deduction, you'll never get to the point. You have to understand the structure of the formula and what is the right strategy to use. Okay, so suppose you know P implies Q is true, and you have to prove not P or Q. How can you prove this fact? So let me give you a hint. Use law of excluded middle. And I'm going to actually give you that exactly. Use not, P or not P, and use two cases. When P is true and not P is true. Okay? So, what happens? Suppose P is true, and you know P implies Q is true. What can you derive? Q. You know P is true, P implies Q is true, then Q can be true, right? If Q is true, can you derive the last formula? If Q is true, can you derive this one? Yes, how can you do? Disjunction introduction, right? If you know one of them is true, if Q is true, then you can make disjunction with any other formula that is still true. Okay, so nice thing is this, if, so let me write informally. So I know P implies Q is true. And if P is true, then I can use this one to derive Q. And if I know Q is true, then I can derive Q, not P or Q. Okay, so this is my first case. If P is true, somehow I can use with P implies Q, I can derive Q. So from this, I can derive not P or Q. Now the next one is, what about not P is true? Immediately, you go this. Why? Because not P is one of the disjunctive terms. This is true, so not P or Q is also true. So let's write down this proof in natural deduction. So what you see in this informal description is you need case split. Okay, so when say P is true and P is false. So let's see. If P is true, okay, so this is actually the case split. I need two cases, right? Do you remember the OR elimination? We are going to use OR elimination for line 2 and these two boxes, right? So in order to use this OR elimination, I have two case split. So when P is true and not P is true. Okay? When P is true, using 1 and 3, I can derive Q. Okay, this is assumption, Zerian premise. I can derive Q in line 4 by using implication elimination for lines 3 and 1. Right? So using 3 and 1, okay, I know P is true, and also P implies Q is true, so I can derive Q here. Okay? And once I have this, I can use OR introduction for line 4. So this is line 4. So we proved not P or Q. Okay, so case 1, we proved not P or Q. Okay? Also in case 2, we need to prove not P or Q. How can we do this? This is assumption. 7, this is actually immediate because not P is already true, so not P or Q is also true by OR introduction for line 6. And since we established all the things that is needed to prove the, to use OR elimination, we are done. This is 3 to 5, and this is 6 to 7. Okay? All right, so let's go through this proof again. This is a bit non-trivial. Maybe the most difficult part for the people who learn this natural deduction first time is that we use this law of excluded middle. Okay? So once you do some practice, this actually becomes quite obvious what you have to do. But for the time being, it's like algebra. Okay, you have to simplify the equation and so on and so forth. Basically, you need a practice to do. Okay, so like factoring out, you need a big practice. Same thing here. So we know the premise is true, and we know we can use the law of excluded middle. Then case 1P, from this we can derive Q. So we have not P or Q to be true. Case 2 not P, okay, we can also derive the same conclusion, not P or Q. Now these two conclusions inside the boxes was possible because of all cases. So the conclusion can be outside the box as well. So that's the last line here. Okay, any question up to this part? Okay. So if you got stuck in what rule to use in natural deduction, think about some informal way how you can utilize this information. Okay? Okay, so now we have the 4 natural deduction rule. And as I said, you are allowed to use any of the deduction rules, primitive or derived, I don't care. Okay? So you have 14 rules to use. In fact, if you don't want to memorize all 14, I definitely want you to memorize 10 and try to derive 4. Okay? But if you don't mind, then you can memorize all 14 rules. Sometimes that could be easier to solve some problems. All right, so going back to the question that you raised. So in the proof, we see assuming something, we derive some formula. So for example, here, this was actually one of the examples that we saw before. So we can actually prove by assuming P and Q implies R is true, we can derive P implies Q implies R. But we can also assume the other side and prove the other one. Okay? So instead of deriving this, we can assume it and we can prove this. Which means that you can go from one formula to another. So given this formula, you can derive another formula. And given the other formula, you can derive the original formula. So in that case, what you can say is these two formulas are so-called provably equivalent, because you can derive one from the other. And sometimes we use this notation to say that they can go in both directions. Okay? And in the homework problem, I gave you some problems in this case, or provable equivalence. There are some problems I skipped. I give you only prove one direction, but there are also other directions that is also possible. Okay? All right, any question before we move to the next subject? Okay. So the next topic that I want to talk about is proof. There's something called constructive proof and something called non-constructive proof. Okay? And we are going to utilize the idea of natural deduction to some proof that is not only with respect to propositional formulas. Okay? This is more practical use of natural deduction. The first thing that I want to talk about is in the area of logic, there was something called Intuitionistic Logic. And these people who advocate Intuitionistic Logic didn't like some of the axioms that you learned so far. Okay? So for them, they didn't approve some rules in natural deduction. These are the rules that they didn't like. So PBC rule, LEM rule, not double negation elimination rule. These are the rules that they think should not be there. And this is a bit hard to understand why, because it makes quite good sense, because every time either phi or not phi is true, and you can always eliminate or introduce double negation. What is wrong with this idea? Okay? So to illustrate their point, let's look at an example. So it's about rational number or irrational number. So first, let's remind us what is a rational number. The definition says a rational number is a number that can be represented in form of fraction where numerators and numerator and denominator are integers. Have you seen this before? Then what is an irrational number? Irrational numbers are the numbers that cannot be represented by this fraction, right? Can you give any example of irrational number? Pi. And other things? Sorry. E, okay. What else? Square roots of 2, right? How do you know that these are irrational? How do you know? How do you know that these numbers cannot be represented by the fraction? Well, rational numbers are easy to prove, right? How do we know that number 2 is a rational number? It's a 2 over 1. Okay? How do you know that 3 over 2 is a rational number? It's basically fitting the definition. But how do we know that square root of 2 is an irrational number? How do you know that this square root of 2 cannot be represented by, no matter what p and q that you use, you cannot write it as a p over q? How do you know that? Anyone? Okay, good. So we'll look at why today. Okay, so let's actually practice. Actually, I don't have to use Socrative, right? Okay, so what are the rational numbers? B and C, right? Why C is a rational number? Because there's 2 over 3, yes. So the answer is B and C. Okay, but what this example is saying, why for some numbers like 0.666, we can represent it as 2 over 3. But why square root, we cannot represent it as some number q over p? What is the difference? It does not repeat, but how do you know? Who knows? It may repeat. Maybe eventually, how do you know? Did you compute, like, how many digits did you compute, right? Okay, so we'll see a much better way to prove that claim. So one of the examples for this non-constructive proof is this. There exist irrational numbers a and b such that a to the power b is rational. Okay? So can anyone give this number a and b? So this number a and b must be irrational, but when you make it a to the power b, suddenly it becomes rational. Can you find that number? Okay. So let's think about this. There's actually proof of this claim. Okay. The proof goes like this. It actually uses law of excluded middle, which some logicians didn't like. Let me write the proof in the form of natural deduction. Okay, so this is not the typical proof that you see in the mathematical textbook because they write in formal English. They don't write in this formal level. But let's try to write this in terms of natural deduction. So one thing that we are going to use as a lemma. Lemma is a small claim that is not the main claim that we want to prove, but it will help us to prove the main claim. So we call those statements as lemmas. So lemma 1 here that we are going to use is square root of 2 is irrational. And we are going to prove it later. Okay? But assuming this, we want to prove the claim that I showed in the previous slide. There are 2 irrational numbers a and b such that a to the power b is rational. And I'm going to quiz you after this proof whether you actually understand what is going on. Okay? So the proof of this theorem goes like this. Case split. So law of excluded middle. The claim is this number is either rational or irrational. Okay? This is law of excluded middle, right? Whatever the sentence is, the sentence square root of 2 is rational. This is like an atom P. It can be true or false. It's a declarative sentence, right? We can say either P or not P is true. Are we together? P or not P is true, right? So what I'm going to do is to use the OR elimination. So case 1, I'm going to draw a box. Okay. two boxes. Okay. Let me actually call this whole thing as P. Okay? So the whole sentence that exists irrational numbers a and b such that a to the power b is rational is one sentence P, because this is either true or false. It's a declarative sentence. So what this LEM is saying is actually P or not P, right? And case 1 is assuming P, okay, which is square root of square root 2 is rational. And case 2 is this number is irrational. Or is actually, yeah, let me just write this way. So square root negation of this number is rational is same as this number is irrational. Okay, are we together? Okay. So in each of the case, what we are going to prove is the claim P holds. So I'm going to show that P is true, so that P is true, whichever case that we are in. This is the proof structure. Let's first agree on the proof structure. Okay, so I'm going to use P or not P as a law of excluded middle. Case 1, assuming actually not the P, let me write. I mixed up this. Let's say this thing as statement. So we are going to prove this statement, and this one is our P. Okay, so we assume this number is rational, and try to prove that there exists irrational numbers a and b such that a to the power b is rational. Okay, and case 2, we assume not P. So this is P, this is not P. We'll prove same claim S. And using the OR elimination, we can derive S. Are we together? Do you see the structure in terms of natural deduction? I didn't use any fact about irrational numbers and so on. I didn't use anything, but this is just based on the structure of the statement. I can write this proof structure. Okay, so so what we are going to prove is when you assume this number is rational, we are going to prove this S. And we also, when you assume the negation of P, we are also going to prove the same S. And from this, we'll conclude S, no matter what case that we are in. Okay? So let's look at the proof. So far I didn't use any particular knowledge about the rational numbers, but now we can use. Case 1, so we know that this number is irrational. Let's take a and b to be square root of 2. What happens? Can we now prove S? First, are a and b irrational? Yes. Why? By lemma 1, right? How about a to the power b? Is it rational or irrational? A to the power b. Okay. So by lemma 1, this a and b are irrational, right? Now what about a to the power b? This is square root of 2. Is it rational or irrational? Yes.
Couldn't it be either?
No.
Because there could also
No, no, no.
exist rational numbers.
No.
It says that there exist
Inside the box.
but
No, no. Inside the box. What do you know so far? It's very obvious. Just look at the box. You have only one thing to say in the box.
we had assumed it was rational.
Yes. We have assumed that this is rational. This is a fact now. This is true. Okay? This is rational. This is what you see in 2 lines before. And that is by case assumption. Okay? Hence, this S is true. S was, I'm not going to write the whole sentence S here, but there exists A and B such that A and B are irrational, but A to the power B is rational. The interesting thing is, how do we know that A to the power B is rational? We didn't actually prove anything, but by the case assumption, this is rational. Okay, note here that when we are in the box, we assume something that is in the box as well as outside the box that appear before are assumed to be true. So we can say that they are true. Okay, good. Now for the case 2, I'm going to change A and B to be this way. I'm going to use this as A and use this as 2. Okay? Can you prove S from this? First, is A irrational? A is irrational. Why? By case assumption. B? Is B irrational? By what? Lemma 1. We didn't prove, but let's assume for the time being that it's true. What about A to the power B? This becomes square root of 2 to the square root of 2 to the power of square root of 2. And the algebra tells us that this can be multiplied, and this is actually 2. And this is rational. 2 is a rational number because 2 can be written as 2 over 1. So this S is again true because we found 2 numbers A and B such that both of them are irrational, but A to the power B is a rational number. Okay? So by the disjunction elimination rule, we don't know whether square root of square root 2 is rational or irrational, but regardless of the case, we can prove the given claim. We are done. Okay, so let me go over this proof again. This is a bit non-trivial, but it actually perfectly fits the natural deduction. So first, what do? We assume either this fact or that fact or negation of that the fact is true. This is by law of excluded middle. Either P or not P is true. Okay? Case 1, if P is true, we can say that A and B to be square root of 2. And we know that square root of 2 is irrational numbers. So we found 2 irrational numbers A and B, okay, square root of 2, such that A to the power B is rational. Now this is interesting part. So square root of 2 to the power of square root of 2 is rational. We didn't prove it, but we assume that this is true. Okay, so by case assumption that this number is rational, so what we did is we found 2 numbers A and B that satisfy this statement S. In case 2, we assume that this is irrational. then take A to be this number and take B to be this number. Because the given statement didn't say what should be A and B. It says there exist irrational numbers A and B such that A to the power B is rational. So if we take A to be this one and B to be this one, we know that A is irrational because that's what we assumed in case 2. And square root 2 is still irrational because lemma 1 still applies. But when you do A to the power B, by algebra, it becomes rational. So again, we found two numbers A and B that satisfy the given statement S. So we prove that S in the same case statement. So by the OR elimination, regardless of which case that you are in, you can still prove the same S. So we are done. Okay, so who? I should erase this now. So the question is, so based on the proof, which numbers qualify for A and B? I think you can construct this, so let me erase this. Well, I don't know whether you can read. Let me write here. So based on the proof, which numbers qualify for A and B? So choice A is square root of 2. Choice square root of 2 to the power of square root of 2. B is this. C is not enough information. So let's do the quiz here. Okay, so we proved this claim. So what is this A and B such that A to the power B is rational?
My choices on soccer were A is 1 and then all the way through F being 6.
Sorry, maybe something is wrong.
I meant something.
Okay, let's do again. Maybe I clicked wrong quiz. Okay, if you have typed already, please do so again. I changed the answer type. This should be correct now, right? You should see A, B, C, D, E. Okay, so let me close. Some people still didn't answer. Okay. All right, so let me show you the result. Okay, so most people chose C and B. and most of them are wrong. Okay? So this proof, when you see this proof, okay, so which number qualify for this A and B for the theorem? The proof actually does not establish what numbers that are irrational such that A to the power B is rational. We didn't find that particular number. Okay? The reason for that is we assume by case split that this is rational or irrational, but we didn't actually prove that fact. Okay? So in case 1, this number square root of square 2 is rational. In case 2, this number is actually irrational. Okay, so you cannot say which number fit the A and B for this theorem. Okay, the reason that this comes out is a bit tricky to understand. The main idea that this proof becomes non-constructive is because of the law of excluded middle. So this proof is non-constructive. Why? Because the proof was saying, the statement was saying that there are these numbers A and B, but the proof did not construct what A and B qualify for this statement. Okay, so we know there exist two numbers. There exist some numbers A and B that satisfy this theorem, but the proof did not establish that. Okay, so constructive proof, on the other hand, should establish what these numbers are. Okay, but this particular proof does not show that. Okay. All right. So this kind of proof is actually not very rare. So sometimes you see there exists epsilon such that for some range of delta, some property is met, but you never actually show what is that epsilon and delta. Okay. So such proof is actually non-constructive. Now, some people who work on this constructive proof idea, their main idea was if you do not allow these rules to be used in the proof, then the proof will be constructive. So you will not have this kind of proof that you just saw. Whenever such the statement was saying that there exists A and B, such proof that do not use these rules should show what are these A and B. Okay. All right. So that's about it. So I have actually one business here, which is to show that square root 2 is irrational. But I guess that proof is a bit more challenging. So let's postpone it to the maybe next class. Okay. So having seen one complicated proof in one day should be enough. Okay. So let me skip this fact. Okay, the next topic that I want to go into, so today we are going to start this, and we probably don't have time to finish completely, is the induction. Okay? So, here's a typical thing that I see. When you have to prove the mathematical claim. So here you're given these recursive definition. So f of 1 equals 1, and f of x plus 1 is equal to f of x plus 2x plus 1. Okay? So if you compute these numbers, f of 1 is 1, right? Now f of 2 is f of 1 plus, so f, okay, f of 1 equals 1. F of 2 is f of 1 plus 2 times 1 plus 1. And this is 1 plus 2 plus 1, which is 4. And you can do the same for the other cases. So f of 3 is equal to f of 2 plus 2 times 2 plus 1. This is 4 plus 4 plus 1. This is 9. And if you do this thing, you will see that these are the squares. Okay? When you try f of 1, 2, 3, 4, 5, then you will see that the numbers are the squares form. So you say this as conjecture, f of x is x squared. Okay? So some student claims that this is the proof. What is wrong with this idea? What is wrong with this idea? So this is your proof, right? I ask you to prove that f of x is x squared. So you just show some cases, right? And you say that this is the proof. What is wrong?
Is it just a few examples?
It's just a few examples. The claim, yes, the claim is f of x should be x squared for all possible x, but you show only a few of them. And you may say, what's wrong with that? It may end up satisfying this thing forever, right? In fact, some mistake happened some time ago. So people realized that there's a pattern here. It's 2 to the power of 2 to the power of 1 plus 1 is 5. 2 to the power of 2 to the power of 2 plus 1 equals 17. 2 to the power of 2 to the power of 3 plus 1 equals this. So it looks like a theorem or conjecture that if you have 2 to the power of 2 to the power of x plus 1, that it becomes a prime. Okay? That makes sense for the first 4 numbers here. But it turned out that actually the next number is not a prime. That's very hard to compute. Note here that this was in 1600s, right? So to compute this number, to identify this number is a prime or not, I mean, he doesn't have a calculator. Okay, it looks like a prime number, but it turns out that this is not a prime number because it has 2 factors, which is not 1 in itself. Okay? So having some examples is never enough. Even though it may be true for maybe first million cases, doesn't necessarily mean that this is true forever. So how do we prove this kind of claim? You cannot. So suppose I ask you to prove this by prove this. Okay, you cannot go over all the cases because there are infinitely many numbers for x, right? But you have still finite space and finite time. So how can you compute this claim? So this is where the induction comes in. And you may have seen this induction principle before. Okay? So what is induction saying? The induction has the parameter n. So it is a statement, some declarative sentence P, but it has a parameter n. Okay? So to prove P of n is true for all natural numbers greater than or equal to 1, we show these 2 cases. One is so-called base case, prove that P of 1 is true. And the other case is inductive step. If P of m holds, then P of m plus 1 holds. If you can show these 2 cases, then you can claim that P of n holds for all numbers n. That's induction principle. Okay? So what is going on? Maybe let's actually show you the proof in induction. Okay? So I want you to remember this pattern. Okay? I'm going to explain why this is enough. But for now, if you can show these two things, then you can show that the property P holds for all values of n. So this is one of the examples. When you prove by induction, you have to identify what is the statement that you are going to prove. Okay? So the claim to prove is this. And I'm going to write this as P of n. The reason for that is this claim depends on what number n that you choose. And this is a declarative sentence. It's either true or false. Okay? So the base case is to prove P of 1 is true. And the inductive step is if P of m is true, then P of m plus 1 is true. Induction principle tells us if you prove each of these two claims in two cases, then we are done. This property P holds for all values of n. So let's first see whether this is actually true. So P of 1, is it true? How do we know that? This is actually easy because this is P of n. So what is P of 1? Look at the P of n and look at P of 1. So what does P of 1 means? N equals 1, right? If n equals 1, what is the left-hand side? 1 plus 2 plus up to n. If n equals 1, what is the whole sum here? Just 1. When n equals 1, what is the right-hand side? 1 times 1 plus 1 over 2. Is this true? Yes. Right? Simple algebra tells us that the left-hand side is equal to right-hand side. So P of 1 is very easy to prove. Now, for the inductive step, we are going to assume that this is true. Assume 1 plus 2 plus m equals m times m plus 1 over 2. Don't ask why, because that's not your job. This is what you assume to be true. Now, what you have to prove is the goal. The goal is to prove 1 plus 2 plus m up to m plus 1 is equal to this number. Now, note here that this goal has not been proven yet. Okay? But this is assumed to be true. You have to assume to be true, right? You don't have to worry about whether this is being true or false. So let's try to prove this goal. So if you look at 1 plus 2 plus up to m plus 1, I'm going to divide into two parts, up to m, and then m plus 1. And I know that this part is equal to some simplified form. I know that this is equal to this. So instead of this, I can substitute this for this. So I get 2 to the m times m plus 1 over 2. Okay, so I'm just replacing this with this. I still have to keep this m plus 1 here, right? Are we together up to this part? Okay, so what I'm going to do now is I'm going to multiply 2 to each numerator and denominator so that I have the same denominator. If you want to add fraction, you have to make the denominator to be the same. And I'm going to add these two numbers, but they have common factor. What is the common factor? Let me just repeat then. These two terms have the common factor. What is the common factor? M plus 1. So I can factor out. So m plus 1, and then I have m plus 2 left over. Now this one is exactly what we had to show. So we are done. So we started with this one, 1 plus 2 plus m plus 1 equals to this number. This was exactly the goal to be proven. Okay? So we proved P of m plus 1 is true. Okay? Good. Any question about this proof? Yes?
Where did you get the 2 times n plus 1 again?
This one?
Yeah.
So we have m plus 1 here, right? And m plus 1 is equal to 2 times m plus 1 over 2, right? Because I multiply 2 to each numerator and denominator. Okay? So m plus 1 here is equal to this guy. The reason that I changed to this because I want to make 2 to be the denominator so that I can add these two numbers. Okay? So by induction principle, if we prove these two facts, that we are done. Okay. So here is another proof. Any set of n horses have the same color. Okay? And we assume that each horse has only one color. Okay? So proof by mathematical induction. So we first need to identify what is P of n, right? So P of n is a declarative sentence that has a parameter n. So the claim here is any set of n horses have the same color. We have to prove the base case. The base case is P of 1 is true. P of 1 here means that any set containing only one horse has only one color, which is definitely true, right? Because if you have one horse, and there's only one color associated with one horse. Case 2. Now we assume the induction hypothesis to be true, which means that if you pick any set of m horses, then they have all the same color. So using the induction assumption, induction hypothesis, we will prove this for P of m plus 1, meaning that m plus 1 horses have the same color. So take any set that contains m plus 1 horses. Okay? Consider the first m horses, h1 through hm. Okay, how many horses are in this set? h1, h2, up to hm. How many horses are there? M horses, right? If there is an m horses, then induction hypothesis apply, because any set of m horses have the same color. So this set has only one color associated. Let's call it C1. Now take the next group from H2 to HM plus 1. How many horses are there? H2 to HM plus 1. How many horses are there? M plus 1? I just shifted by 1, right? From H2 to HM plus 1, there are still m horses. By induction hypothesis, that also applies to this set. So it also has its only one color. So this set has only one color. Call it C2. If you look at these two sets, they have common horses, H2 to HM. And each horse has only one color, which means that C1 should be equal to C2. The color of the first set should be the same as the color of the second set because they have the common horses. And each horse can have only one color. So we conclude that all the horses from H1 to Hm plus 1 have the same color. So this proves the inductive case. What we did was using the induction principle, okay, we proved the base case, and we assumed the induction hypothesis. The induction hypothesis here is any set of M horses have the only one color. Okay? And from this, we proved that any set containing M plus 1 horses also have the same color. Okay? Convincing? Let me ask you, convincing. Why?
I think the assumption in the third line is an incorrect assumption.
Assume the induction hypothesis, this part?
Yeah, I think it's trying to use
Any set of M horses have the same color. You have a problem with that, right? What about the others? What do you think? Do you agree with him?
I think there's something with.
Do you agree or not? Just tell that first. No,
There's
you don't
anything,
agree.
right?
So I said just in the previous slide, don't question about induction hypothesis. Okay, this is what you assume to be true. Okay? So in the previous page, when I talk about the thing, okay? If P of M holds, then P of M plus 1 holds. When you prove it, P of M is inside the box. Okay? So it's basically you're proving P of M and then try to prove P of M plus 1. This is assumed for the time being. Okay? And for this kind of assumption, you cannot question about it. Okay? This is what induction principle allows you to do that. Okay? What the induction principle is saying that if you can establish these two facts, first proving the base case, second assume the induction hypothesis, and then try to prove P of M plus 1. The confusing part is P of M and P of M plus 1 have the same structure. The only difference is the parameter. In induction hypothesis, you are given M. In the goal, in the inductive step, you have to prove for M plus 1. Okay, so when I show you the proof here, okay, this part was assumed to be true, right? I told you, don't worry about it. That's what induction principle allows you to do that. I'm going to explain a bit more about why this is safe to do. Okay? But what the mathematician found was this is okay to do. You can assume the induction hypothesis is true, and then using the sound reasoning here and can prove the next case, then you can say that this property holds for all values of M. And the proof here is following the same structure. It proves the base case, okay, P of 1, and it assumes the induction hypothesis, and then prove this. So the numbers, the line 3 is actually okay. All right, let's do some quick idea here. So multiple choice. Let's have a guess, and maybe I'm going to explain this later. So, or if the majority find the answer, then I can just speak out. Okay, so what is wrong among these four statements, A, B, C, D? Well, maybe this claim is true. The statement is true, right? If you pick any set of M horses, they always have the same color. All right. Let me say that C is the majority, but that's not correct. So I'm going to tell you later. Okay? So let's open the exit ticket. And if you need more time, think about it.